In this video, we continue with the chapter 2.4 examples. We take a look at the definitions of lower triangular and upper triangular matrices and some theorems associated with elementary matrices and invertibility. We say a square matrix that we call L is lower triangular if all entries above the main diagonal are 0. So in this diagram down here, you've got matrix L, and you can see the zeros are in row 1, column 2. So we call that the 1, 2 entry. In row 1, column 3, and in row 2, column 3. So we can also define this as saying the, ijth entries, here they say Lij equals 0 when I is less than j. So when the rows are less than the columns, that's where our zeros are. In this matrix L down here, the x's just represent numbers that you could fill in for those values. So next we see matrix U, which is considered upper triangular. So again, it has to be a square matrix. And then we say a square matrix is upper triangular if all the entries below the main diagonal are zeros. And so we'd say, all right, an entry Uij is 0 when the number of rows, the row number is greater than the column number. So we've got zeros here in row 2, column 1, row 3, column 1, and row 3, column 2. And then we say a square matrix is diagonal if all the entries not on the main diagonal are 0. So we say entry Dij is 0 whenever I and j are not equal. So here we just have entries in positions 1, 1, 2, 2, and 3, 3. Okay, so Theorem 2.13 tells us about elementary matrices and the relationship between invertibility. So I added a little bit extra here, so I call this Theorem 2.13 plus. So if E is an elementary matrix, then E inverse exists and is also an elementary matrix. Moreover, if E is a lower triangular matrix, then its inverse is also lower triangular. And if E is diagonal, its inverse is also diagonal. So here's an example. We had matrix E1 from the previous example where we swapped row 1 and row 2. Well, think about if you're multiplying a matrix and you're swapping out row 1 and row 2. If you want to go backwards, you want to swap row 1 and row 2 again. So E1's inverse is just itself. Swap back row 1 and row 2 and you'll end up with the original matrix. Matrix E2 multiplied row 1 by 3, added that to row 3 to form a new row 3. So think about working backwards. E2 inverse has a negative 3 times row 1, adds that back to row 3, and that replaces a new row 3. So you can think about, oh yeah, subtracting out that 3 times row 1 value is going to bring each entry back to the original row 3 entry. And then our matrix E3 took row 3 and multiplied it by 1, 6. And so the inverse of that matrix to bring us back to the original matrix would be 6 times row 3. And then you can verify these using matrix multiplication. If you multiply these by their inverses, you get the identity matrix back out. So you can double check right there. Because elementary matrices are formed using the identity matrix and then manipulating it with one of our row operations. So here we see E2 times E2 inverse gives us back out the identity matrix 3 by 3. And then here is E3. Oh no, sorry, that's E2 again. That's E2 inverse multiplied by E2, also giving us the identity 3 by 3 matrix. All right, Theorem 2.14 says that invertible matrices are row equivalent to the identity matrix. So remember, a matrix is row equivalent if we can multiply it by elementary matrices to get the resulting matrix. So 2 matrices are row equivalent when one is the product of elementary matrices. So a square matrix A is invertible if and only if it is row equivalent to the identity matrix. So here's A, our square matrix, and we're going to show that it is row equivalent so that it equals these n elementary matrix operations multiplied by the identity matrix. And notice in the second equality, we don't need to write out I for identity matrix because that's not going to change our product. So we can just write A equals elementary matrix and multiply through all the way through the first elementary matrix. So this is if and only if A is a product of elementary matrices. So we're saying, okay, we are going to say A is invertible if and only if it's a product of elementary matrices. So we are going to start with the forward direction first here in our proof, and then we'll do the backwards direction down here. So we are going to start by assuming A is invertible, and then we are going to show that A is a product of elementary matrices. So since A is invertible, we know back from Theorem 2.11 in section 2.3 that AX equals B has a unique solution, and we showed that that could be written as X equals A inverse times B. So this means that we can use row operations to reduce A augmented with B to the identity matrix augmented with C, where C is A inverse times B. So if the corresponding elementary matrices are E1 through En, then the identity matrix is En minus 1, and so on, multiplied through by E1 times A. So then we can say, well, A is just E1 inverse multiplied by E2 inverse. Note the order is changing in our multiplication because of that property of matrix multiplication through En inverse, which is a product of elementary matrices. So we have shown that if A is invertible, then we can write it as a product of elementary matrices. To go backwards, the other direction of the proof, we start by assuming A is a product of elementary matrices, and then we're going to show that A is invertible. So here we've got A as this product of elementary matrices. Then we know, well, the inverse exists because it equals all of these inverted and multiplied. And remember, we're multiplying in the opposite order. So we have En inverse times En minus 1 inverse all the way through E1 inverse. And that is true because we've shown that every elementary matrix is invertible. Okay, so that theorem plus the theorem 2.11 that said that if A is an invertible matrix, then there's a unique solution to AX equals B, allow us to write these equivalent conditions for invertibility. So if A is a square matrix, n by n, then the following statements are equivalent, meaning if one is true, then the others are all true. So we could say A is invertible. We can say AX equals B has a unique solution for every column matrix B, or you could think about it as a column vector B, since it's got just one column there. AX equals 0 has the only trivial solution. Based on what we just showed in the previous proof, A is row equivalent to the identity matrix in the same dimensions, n by n. And then based on what we just proved, A can be written as a product of elementary matrices. So we can treat these as equivalent. Okay, in the next video, we're going to look at how we can do factorization with lower and upper triangular matrices.